Good evening, everybody. This is a strange looking problem because in base 10, any numeral that ends in 5 is certainly divisible by 5. Let's go ahead and write subscript 10 here, even though it's normally omitted. Okay, this is equal to what, 5 times 23? And so it's manifestly divisible by 5. There it is. 5 times 23 is 115. Another way to write this is 115 is congruent to 0. I'm leaving the base out this time right here. It's congruent to 0 mod 5. Okay. Now, we're dealing with a different base down here, base 7. And it ends in the digit 5, which is a permissible digit in base 7. But we want to show that it's not divisible by 5, which seems counterintuitive, but it does show you that divisibility depends on the base, the number, the system of numeration, I guess some people call it, okay? So we're going to show that this is not congruent to 0 in base 7, all right? Now, a super helpful result here, 7 is congruent to 2 mod 5. Trivially, 7 minus 2 is 5. This generally means a multiple of 5, but 5 is a multiple of itself, right? Now, one of the nice benefits of writing divisibility in this fashion is we can treat it just like an equation. You know, like regular equality, you can multiply equal equations against equal equations and get another equal equation. It's the very same thing. It's the very same thing right here. Now, we better go ahead and say n is greater than or equal to 0. These statements wouldn't make any sense if we allowed for negative integers, since these would become fractions. Okay. Now, we can also write the expansion of our number here. It's not base 10, it's base 7, and that takes a little bit of getting used to. Most people are used to base 10, but we are doing base 7 here. Okay, but this is the expanded form, what's called the expanded form of this numeral, this base 7 numeral. Okay, now we're going to successively use this property that 7 raised to the n is congruent to 2 to the n, which does follow from this statement. This kind of stuff is proven in an elementary number theory course. I'm just going to take it as face value that it's true right now. Okay, but so what we can do on the very next line is notice how the equal sign gets replaced with congruence. Y'all, it's understood it's mod 5. I'm not writing mod 5 down to avoid clutter, but it's understood to be mod 5. So again, notice, and I put the 1 here just, I know it looks superfluous, but just to account for all the 1s here in the expansion. Okay, now, so 7 gets replaced with 2 in all these locations. 2, 2, 2, 2, and the congruent symbol. You see the congruent symbol, not the equality symbol. Okay. Now, why is that important? Well, it's just easier to compute 2 to the 7th and 7 to the 7th, right? Okay. So let's go across here. Now we have equality. This 128 is equal to 2 to the 7th. 64 is equal to 2 to the 6th, and all the way across, right? This would be 2 cubed right here. This would be 2 to the 4th, and all the way across, folks. Now, the very next line here, I'm going to go ahead and do congruence. Let's replace, we'll go congruence. And y'all, again, we are talking mod 5, okay? It's just cleaner to not write all that down. Now, notice that 128 leaves a remainder of 3 when you divide it by 5. 64 leaves a remainder of 4 when you divide it by 5, and so on. Right. Now, what about 5 leaves a remainder, or 8 leaves a remainder of 3 when you divide it by 5? Plus 4, plus 2, and now some of the magic of congruence. 5 is congruent to 0, right? So we can put plus 0 here. That's nice, isn't it? Okay. Now, let's keep going. It's really kind of nice how this stuff piggybacks on itself. 3 plus 4 plus 2 plus 1 is 10, but 10 is divisible. 10 is divisible by 5, obviously. So we replace this entire part. This entire piece gets replaced by 0. Okay. Now right here, we have plus, this would be 9. Well, let's just write it out. Okay, plus, I'll come over here and put the plus sign right here. This would be 9. All right, folks, 3 plus 4 plus 2 is 9. But 0 plus 9, of course, is equal to 9, and that's congruent to 4. See? Pretty nice. So this result here makes the computations much easier. It's much easier to elevate 2 to higher powers than it is 7, right? And so you see, this is not, let me just put, it's not congruent to 0, right? And that's the only way the numeral would have been divisible by 5 is had it been congruent to 0. So we've proved that we can just write QED if you want to. The only way it would have been divisible by 5 is if we had gotten 0 right down here, but we got 4, which is certainly not congruent to 0. Okay, so that does it, folks. It's not divisible. That's the proof. And again, I think it's kind of neat because you're so used to seeing a last digit of 5 and thinking, oh, it's divisible by 5, you know. But it does depend on the base that we use. So we've used the, and think about how big this would have been. This would have been the 7th position. This would have been 7 raised to the 7 right here. See, just this position alone is 7 raised to the 7. This position is 7 raised to the 6. A very difficult computation. You're adding all these up. Very difficult direct computation. Some people try to convert it to base 10 and then do all the work. But here we used a nice reduction aid with congruence arithmetic. Okay, that's all I have for you.